Hello there, ladies and gentlemen. Welcome to another episode of Fun Times in Calculus. I'll be your host. I'm trying to sound like a YouTuber. How's it going for you guys? It's great. I am awkward as all holy, as usual. So today we're going to be talking about section 9.6, also known as Let's Get Integrally with It. So up until now in multivariable or multidimensional calculus, we've only done some derivative action. Today we're going to update what we can do and what we understand by looking at integration. So the first type we're going to look at is looking at integrating in just one direction for one variable. Those are known as, this says double integral. This is, oh, because that's the name of the section. Sorry. So we're going to first up do single integrals of two variables. I will correct this on your notes so you have the right thing. But basically what this is it's a lot like a partial derivative. If I have both x and y inside my integral, but I'm only integrating with respect to x, like looking at a, it's got y and x in it, in y minus 1 divided by the square root of x, but it's only being integrated in the dx direction, we're going to treat all variables as constant other than the one being integrated against, or the integrand we're only going to be doing in terms of the differential. So we're only going to be paying attention to that d variable. Just like all things in life, it's the d that matters. That was bad. Yep. Only integrate the differential variable. And you'll see me do this. Allergies like whoa. All right, here we go. So essentially, since this is with dx, I'm going to ignore the fact that y is there. So let me rewrite this in a way that sort of reflects that. So I'm integrating from 1 to 4. I've got y minus 1 times 1 over the square root of x dx. So one more rewrite and then I'll be good to go. 1 to 4, y minus 1. So I'm treating y minus 1 like it's a constant, like I had a 3 sitting there. X to the negative 1/2 dx. Cool. So then I'm going to go through the process of integrating with only respect to x. So I'm going to ignore this y minus 1 factor. It's just going to come along for the ride. And then I'm going to integrate x to the negative 1/2. So you add 1 to the power. So negative 1/2 plus 1 will give me a positive 1/2. And then divide by that factor. So divide by 1/2 and evaluate from 1 to 4. So let me clean this up a little bit. So dividing by 1/2 is the same as multiplying by 2. Y minus 1. And then 1/2 power, that's the same as the square root of x, evaluated from 1 to 4. So let's go ahead and put in our values. So I'll have 2 y minus 1 times the square root of 4, which is just going to be a 2. Why am I putting a parenthesis there? It doesn't make any sense. Minus 2 y minus 1 times the square root of 1. And I did it again. What is with me today? Okay, square root of 4 is going to be a 2, so I'm going to end up with 4 y minus 1s for that first one. So I'm taking this, calling it a 2, and multiplying by 2. And the square root of 1 is just going to be a 1. We know that adding a 1 doesn't really do anything. So I have 2 times y minus 1. So if I have 4 minus 1s and I lose 2 of them, I'm left with just 2 y minus 1s. Hopefully you followed that okay. No big deal. Notice there's no plus c here because, well, I evaluated in terms of x. It's actually a definite integral. Let's do another one so you can see how this goes. Now notice I have the same integrand. I have the same stuff I'm going to be integrating, but I'm going to do it with respect to y this time. So I'm essentially going to be ignoring that square root of x. So I'm going to rewrite this just like I did before. Integral from 0 to 2. Oh, it's in a different direction. I've got a different amount of values I'm looking at. And we'll see that coming up when I start doing other things. So I'm going to rewrite this as the square root of x times y minus 1 dy. It's very important that if you've previously been somebody who I've written notes about how, hey, don't drop your differential, don't lose your d, that you make sure you don't do that for these because it makes it very clear which variable you're integrating. I'm integrating y, not x. And that's one of the reasons why they've been an essential part of our integration steps. Okay, so I'm going to go ahead and integrate. So the 1 over square root of x, it's just going to come along for the ride because it's not being integrated. And then I'm going to go ahead and do the integral of y minus 1 with respect to y. So I'm going to leave that parenthesis there. So the integral of y with respect to y is I'm going to add 1 to the power and divide by it. Similarly, for 1, I'm going to think of this as y to the 0. I'm going to sneak that in here. Whoop. As anything to the 0 power is going to be 1. So I'm going to add 1 to the power and divide by it. There we go. And then evaluate that from 0 to 2. Oop, got to end my parenthesis. So when you're putting in 2 and 0 into the y variables, not the x, so that's square root of x, or sorry, 1 over square root of x, it's just going to come along for the ride. 2 squared over 2 minus 2 minus 1 over the square roots of x of 0 squared over 2 minus 0. Anytime you end up with a bunch of zeros for all your variables, hopefully you recognize that this is just going to be nothing. Oh, sorry, big yawn. Square root of x. So here I've got 4 over 2, because when you square 2, you'll get 4. Divide by 2, that'll give you 2. Oh no, 2 minus 2. What's going to happen here? I don't know. Well, I do know. It's 0. Woohoo! Because 0 minus 0 is 0. Just to make things clear that this is nothing. I don't know. Hopefully you saw that one coming. It's kind of interesting. So one way you could think about this is that no area underneath this curve in the y direction, or the amount of area from 0 to 2 in the y direction cancels each other out. Remember, you can have negative area. It just means it lies below the 0 plane or the 0 axis. So don't convince yourself that it's not a thing, man. Let's talk about a double integration over a rectangular plane. So this is something that we are going to be doing quite a bit of and is a little bit difficult to visualize, but through the miracle of writing something three-dimensional on something that's flat, hopefully I can help you make sense of this. So I'm drawing our usual XYZ axis, and then I'm going to just draw myself a nice little simple curve up top. Let me do a darker blue because I think that'll look a little bit better. So suppose I've got like a little paraboloid sheet here that's like shaped kind of like a sheet, hopefully. I drew it too big though. Hold on. Let me erase some of this. Sorry about that. It's a little bit too big. I'm going to make sure it fits. Yeah. So I want you to picture this going over like a square region of x and y. Okay, this is too far over because you got to be able to see it. I want to erase the y and make it a little bit further over so I can make a better vision of what's happening here. There we go. This drawing is taking me much longer than I anticipated. I should have just inputted one from your textbook because I want these to be parallel to x and y is the big thing. There we go. Cool. Let's erase this weird part. Done. Okay, so the idea is I've got some range of nope. Hold on a second. Sorry about that. I was having some undo and erase problems. So this is my range of x's, this is my range of y's. I'm making a rectangular region. Say this one is like from A to B. Remember, this is the value 0, 0, 0. So this looks very similar to your three-dimensional objects. And then in the y direction, I'm going from C to D, okay? So remember back in the day when you do an integral and you carve out a little tiny delta x piece and then say like, oh, I'm going to let that delta x get super, super, super small as I head out towards infinity, and that's where dx comes from. We're going to do the same thing with a little tiny delta square. So I want to do this in a different color actually. So say this is my tiny delta y and this is my tiny delta x. And then up here on the curve, it'll form like a little itty bitty sheet. Up on bloop, and z equals f of xy. So hopefully I spent enough time on looking at what z f of xy is that you have a decent picture of this and what's happening. So I'll have like this region of area down below, and I'm looking at integrating over that rectangular area. This is also called iterated integrals, in case you want to look this up in like ancient books. I love it when the random stripes come up when I get the pen too close. Perfect. Cool. So what we're going to have is we're going to have a rectangular region R. Let R be the region X is between A and B, so that's the X range over here, and Y is between C and D. Ta-da! Then the double integral of f of xy over R is, and this is pretty simple, you write it as integral over R of f of xy, and I'm going to do this as dy then dx, and I'll explain what that means in a second, is going to be the integral from, I'm going to have to just use f to make this fit maybe. Nope, not doing it. dy then dx, so that would be, so if I'm going for y first, then it goes from c to d and then a to b. I don't want you to think that matters because you can also do it the other direction, which I'm going to try to shove in here right now. You can go from a to b and then c to d and you'll get the same thing. You just have to do the x integral first and then the y integral. You see me? That's cool. Now what this is going to give you is the volume of f over R. So I mean over, so like on top of. Let me draw real quick what this is going to look like. And this is going to look a little crazy. So highlighter wise, you might not want to draw this. It's like this volume of stuff. Yeah? So I want you to picture like a column of stuff that has this smooth blanket rounded top. Because that's exactly what it is. I'm now going to erase that highlighting because it kind of ruins that picture. Oh yeah, smooth. Kind of fun. Alrighty, let's take a look at doing some double integrals. So, let me scroll up. Hopefully you recognize this from earlier. Essentially what you're going to do with this is you're going to do the x integral first and then the y integral. So just like everything else, you can kind of self-impose your parentheses and say, hey, I'm going to work my way from the inside out. Hopefully that that inside integral you recognize as, well, 9.6.1a. So we've already done the inside one, I just need to do the outside one. So I already did this and got 2y minus 1. And then I've got the dy to deal with still. So I'm going to scroll up really quick just so you can see that yes, indeed, that is what we got. That was this guy right here. A. So what we got right here. Let's use the highlighter so it's more noticeable. I like highlighter. Okay. Less singing when I speak. Okay. Why are there no x's? Well, because we just put in values for x by doing the definite integral back in 961a. Woohoo! So that means we only got to integrate with y. So as usual, we're going to add 1 to the power and divide by it, and then add 1 to the power and divide by it. I'm not dividing by 1, you can't make me. Evaluated from 0 to 2. I really want to clean this up, but I'm just going to wait and do it because I'm just going to substitute some things in. So 2 squared over 2 minus 2 minus, well, a bunch of stuff with zeros in it. I forgot this comes out to nothing. Whoops. 2 times, well, 2 squared is 4. 2 minus 2. Oh, and then divide by 2. Minus a big ol' nothing. Oh, look, it's nothing again. Wonder if that was supposed to happen. Hint, hint, wink, wink. I don't know how to be any clearer about how unsuccessful I am in hiding my opinion on things. Let's do the other version. So, if the world is the right way you think it should be, and you believe my theorem from earlier, hold on, let's scroll back up. Earlier I was like, hey, it doesn't matter which direction you go in. Well, I just did one direction. I did x first, then y, and came out with 0. It should be that when I do y first and then x, it comes out as 0 also, right? Because I just claimed they were the same. Let's find out. Scrolly, scrolly. Well, if you remember earlier, I did this inside integral and got nothing. So I'm going to be integrating nothing with respect to x. Yep. So using what we should do, this should be 0 times x to the 0 power. That looks like a d. Sorry about that. And then, well, oh no, wait, I'm going to integrate. So no, no, no. I'm going to add 1 to the power and divide by it. So 1, evaluated from 1 to 4. That does not look like a 1. Yeah, 0 times stuff is still 0, regardless if you put in 1 to 4. Why am I writing the 4 in here? It's 0 minus 0. It's still nothing. Smiley face. Oh, look, it came out the same. Yay. That's not a shocker. Let's do another one. I don't know if you guys like that one. It's hard to tell when I'm just sitting in a room talking to myself about myself. Yep. Okay, so as usual, I'm going to be doing the x integral first. So again, we're going to ignore the y, treat it like a constant. So this is the same as looking at like an x plus 3. You know what I mean? Good times. But I still have this outer integral on the outside. So even though I'm integrating the inner integral, the outer integral comes along for the ride. So the integral of e to a variable is just e to that variable. So I get e to the x plus y, evaluated from 0 to 3. And then I have dy still on the outside. This might feel real weird to you. Integral from 0 to 2. And then I'm substituting in, so e to the 3 plus y minus e to the 0 plus y dy. Let's clean that up a little bit. Integral from 0 to 2 of e to the 3 plus y minus e to the y dy. And now I'm going to integrate with respect to y. So e to the stuff is still just e to the stuff. There's nothing changing here. Evaluated from 0 to 2. Let's go ahead and do our substitutions. So when I plug in 2 to our integral result, I should get e to the 5th, because 2 plus 3 is 5, minus e squared minus e to the 3 minus e to the 0. Let's clean that up. So I get e to the 5th minus e squared minus e cubed plus 1. That's brilliantly horrible looking. Ugh. Who wrote this problem? Oh wait, it was me. I apologize for my things. I wonder what that is numerically. Kinda don't care. Moving on. Ah, I like this one. Cool. Alright. So remember, doing the inside first, so I'm integrating with respect to x, so the fact that y is in the denominator really doesn't matter. So I'm not going to do anything to the y integrands. So x is just x to the first, so add 1 to the power and divide by it, but don't forget that y was there. Evaluated from 2 to 3. Then I got my dy on the outside. So 1 to 2, 3 squared over 2y minus 2 squared over 2y dy. Ooh, I kind of like this one. This feels like I'm just impressed with myself because I keep on saying things like, ooh, this one's cute, I like that one, I like this one. So silly. So I have 9 over 2y minus 4 over 2y. One thing that's nice about these fractions is they have the same denominators, so I can add their numerators and make it one fraction, which is kind of nice. See why I was excited? So I have 9 minus 4, which will give me 5 dy. I'm going to rewrite this since I have a constant. I'm just going to pull it out front. So 2/5, or 5, sorry, 5/2. Woof. Woof. 1, 2, 1 over y dy. Hopefully you remember that when you do the integral of 1 over y, you get the natural logarithm. So I'll have the natural log of y evaluated from 1 to 2. We're going to substitute that in. 5 over 2 natural log of 2 minus 5 over 2 natural log of 1. The natural log of 1 is 0, so you just get 5 over 2, the natural log of 2. Now if you remember your laws of logarithms, I can use the power rule to hop this fraction into the log, and then you can do this as natural log of 2 to the 5/2, And then if you're really feeling spry, this is totally pointless and I'm just doing it for fun. We can rewrite this in radical notation. This is the natural log of the square root of 2 to the 5th. And you know, you could do 2 to the 5th and get, I think it's 32. And then it's just the natural log of the square root of 32, and I think that looks the nicest. Again, completely for look, not required. I would have been happy with your answer back here, my dear mathematical loves. Ooh, look at this one. All right, so here we have some choices to make. So I've given you the region it's integrating over. And you get to choose who you are going to put first. Do we want to integrate with respect to x first or y first? Now, me personally, anytime I see a 0 popping up, I want to do that one first, because usually it will mean that I get some cancellation and things going away. Now, I just realized this has dx dy, so I have no choice. I have to put dx first. So to do this properly, y is going from 1 to 2, and x is going from 0 to 3, x cubed plus 4y squared, dx, then dy. Now be careful with this one. Remember, we're integrating with respect to x first. So I'm just going to pull this y stuff along for the ride because I haven't done the y integral first, and I'm focusing on doing the integral first, the dx. So for all my x's, I'm going to add 1 to the power and then divide by it, plus 4y squared. There are no x's here, so we'll add an x in, because remember, we think of it as x to the 0 power, and so when we add 1 to that power, we get 1. And we're going to evaluate that from 0 to 3. Now the 0 will be nice because everybody has an x and it's going to drop off, and then we'll dy it. There's no way that's going to fit there, so we'll write it down here. So the integral from 1 to 2 of 3 to the 4th over 4 plus 4 y squared, that y looks weird, x is 3 minus, well, this is just going to be 0 to the 4th over 4 plus 4y squared times 0. This just ends up being 0, so I can just go ahead and ignore it. That's all 0. I want to pay attention to this. Let me rewrite that cleaner. So I have the integral from 1 to 2 of 3 to the 4th power, so that's 81 over 4, plus, and then I'll do 3 times 4 to get 12, y squared dy. So now I want to integrate with respect to y. So I'm going to do the same kind of things, add 1 to the power and divide by it. Can I reduce that? No, 81's not even. I don't know why I was thinking that. Naughty me. Alright, so we're going to integrate. So I get 81 fourths y, because I'm going to think of this as y to the 0. So when I add 1 to the power, I get a y, plus y cubed over 3. So this is going to reduce to a 4, which is nice. And then we're going to evaluate that from 1 to 2. Now, this is where I'm going to run out of space, because life is grand, and that's always something that's happening to me. Okay, so I got to put in 2 and then subtract 1. Yeah, nothing's going to go away, so I'll have 81 to the 4th divided by 4 over, 81 divided by 4 times 2, so that's going to be 81 over 2, plus 4 times 2 cubed, minus, use your parentheses, you don't accidentally subtract something you shouldn't, 81 to the 4th times 1, I'm not writing times 1, you can't make me, plus 4 times 1 cubed, that one I will write even though it's going to come out 1. Anyway, yeah, it's gonna be a number. Okay, so for this, I have two 81 fourths and I'm going to lose one of them, so I really only have 81 over 4. And this is going to be, I'll have 3 cubed, which is 8, times 4, which is just going to give you a 32, and then I'm going to lose 4, so 28. So in the end you get, this is kind of funny, 81 fourths plus 28. And if you do your common denominator in fractions, which I kind of did on the side over here where you guys can't see it because I'm awesome, you get 209 over 4. Or if you like the decimal equivalent, 52.25. Go ahead and feel free to calculate that on your own sweet time. And believe in yourselves and stuffs. I don't know. I should have left more room for that problem. Let's do another one. Ow. Ugh. was I thinking? Well, clearly I was thinking murderous intent. Whew. All right, so dy first this time. That's a fun change. And then dx. Oh, I know why. Because you look at this and hopefully if you're thinking about the y variable, you see some substitution happening. This is going to be kind of fun. I believe in us. So we're going to be doing the integral from 0 to 2 and the integral from 0 to 3 of y square roots of x plus y squared. Wait, do I have that in the right order? Y, then x. Yep. Didn't trust myself for a minute. So I need to make a substitution. So I'm going to change color when I do a substitution because it helps me keep track of when the substitution occurred. So I'm going to choose w to be x plus y squared. Actually, let's just choose y squared. I bet you that'll go better. Cool, because x is constant. It's not going to have an effect. And then dw will be 2y dy. And then I'll divide by 2 so that I get y dy, because I only have a y here, not a 2y. So I'm going to rewrite my integral in terms of w's. So from 0 to 2, and then from something to something, this is now going to be the square root of x plus w dw dx. Now if you like to change your bounds, remember w is just y squared, so if y went from 0 to 3, this is now going to go from 0 to 9, because I'm squaring 3, because y was 3 and now w. If you don't like that, remember you can't always just change back later. Okay, so now I'm going to integrate this. So rather than doing square root, I'm just going to erase this. I'm going to do this as w to the 1/2, because that makes my life easier. Let's add 1 to the power and divide by it. Woohoo! So this will be x plus w. 1 plus 1/2 is 1.5 or 3/2. And then divide by 3/2, that's the same as reciprocating and multiplying. And then evaluate from 0 to 9 dx. This is going to be a big integral, so prepare thyself. So integral from 0 to 2, 2/3, x plus w is 9 to the 3/2 minus 2 over 3 x plus nothing, so I'm not going to write the 0, you can't make me, to the 3/2 dx. Cool. So now same moves, I got to add 1 to the power and divide by it, because I'm going to do it with x this time. So notice I'm moving even further over because I need some space. So I have 2/3. I'm going to add 1 to the power. So 3/2 plus another 1 will give me 2 more halves, which is 5/2 times 2/5. If you want to multiply that out, you can. Minus 2/3 times 2/5 x to the 5/2, evaluated from 0 to 2. Now, for both these, when you put in 0, you're going to get 0. So let's focus on putting in 2. So this is going to be 4/15. Hope you're okay with that. Multiply numerators, multiply denominators. 4/15. When I put in 2 plus 9, that'll give me 11 to the 5/2 minus 4/15. I should have just factored that out since it happened in both of them. Too late now. 2 to the 5/2. Now this one you're 100% going to need a calculator for. There's no denying that that is going to happen. This is approximately 52.753966. I calculated it ahead of time because I was worried about that. 52 came up a couple times in this. Sneaky, sneaky, sneaky. Interesting. Okay, there's where we're at. Alrighty. Alright. Moving onwards and upwards. So let's suppose you want to do a double integral, but maybe you don't want to do it over a rectangular region. So what if your R was in fact not a rectangle? Well, that changes some things. Let me show you. So for instance, if you were looking at your R in the xy direction, your integral, and it was from a to b, but in the y direction it was a function, so it's something kind of curvy, you can still do it over this region. It's just that you have to define things a little bit differently. So this is the region h of x, and then we'll call this lower one g of x. So when you do that, your integral will still be over a, b, and x, but it'll be over g and h, the functions in the x and y direction, or sorry, in the y direction, which is kind of crazy. And you can do this. I'm going to do one over a triangle in a minute, and it actually isn't that bad. Similarly, you can also integrate in the other direction with functions. So here's your x, here's your y, and if you have some sort of crazy wiggly region in the x direction you want to do, this is kind of fun because it looks like I'm drawing people with bad faces, and you're going from, C to D, and those both look like D's. That was awesome. C to D in the y direction, but going from G to H in the x direction. Oops, notice these are functions of y, not functions of x. Usually one of these is easier to do than the other. It will not let me erase, which is weird because normally it has no problem with erasing. Whew. I usually put the constant ones on the outside because it makes your life easier. So these will be the y ones. So this will be from C to D, and then we go from left to right this way and down to up this way. gy, hy, f of xy. Oops. And so for this one, we're going to do the x integral first, and then the y integral second, because these are functions of y in terms of x, which is kind of wild. That part I wrote is unnecessary, so it's just to draw your attention to it. So what they're going to do is when they substitute into your x derivative, or sorry, your x integral, or antiderivative, which is what I meant to say, you'll get rid of all the x's because they'll all have y's in there because these are going to be functions of y. Okay, let me show you what this looks like because this seems like symbolic tomfoolery right up until I do it. Okay, so let me draw you the region R. So notice in the x direction we're going from 0 to 2. I'm going to mark 0, 1, and 2. And then in the y direction we're following from 0 to x, which seems kind of crazy because I'm doing the equation y equals x. So I'm doing it over this region. So you're doing it over a triangle, which is kind of cool. This isn't that bad, I promise. Let me rewrite this because I wrote all over it. Okay, so we're integrating with respect to y first. Yeah, y first, because I'm going da 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 and da 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 da. Yeah, okay. So if you're thinking about like that box idea of what's happening here, I'm doing the I'm doing the y integral first, which says I go from 0 to x. Yeah, so in the y direction I'm doing this way, starting at 0 and then going up to x. And then in the x direction, I'm going this way. I'm starting at 0 and x and going to y, or going to 2. It's kind of weird looking when you write it that way. Yeah, okay. So add 1 to the power and divide by it. Ignoring the outer integral, it's just going to come from the right. We're going to think of this as y to the 0, so it's going to gain a y and go from 0 to x. And then I have the dx integral I'll have to do after. Sorry, it started to look like a dy. So I'll put in x for y. Jesus. dx. So 0 to 2 of x squared dx. Add 1 to the power and divide by it. So we'll have 2 cubed over 3 minus 0, or 8/3. Now, don't make the mistake of thinking that this is area. Remember, I'm doing volume. The 3D picture of this looks like don't let this blow your mind too much. Y equals x, There's my triangle base, my region R. And then I have the function just f of x equals x, which forms a cut plane above this. And it gives you the volume of like this prism shape that has an angle on it. This is hard to draw. Yeah. Maybe don't think too much about that. If you'd like to see a drawing of it, go back to the 3D graphs that I gave you a bunch of apps for, and you can make it do it a little bit easier than trying to draw it by hand. But it's a volume, so this is cubic units rather than just, you know, area. Oh boy. Okay. Let me draw you this one. So in the x direction we go from -1 to 1. So I gotta make sure I fit that in here. -1 to 1. And then in the y direction we have, oh, that's kind of horrible. X equals y plus 1. Okay. So when x is 0, y will be -1. Interesting. And when x is 0, y will be +1. Okay, I see what this looks like. So I'm going to place 1 here. Actually, I need to place it a little bit lower so you can see what this looks like. Whoops. Get close. I'm having a hard time with this. X equals y plus 1. So that's going to be the same as the line y equals x minus 1. Oh, that's easier. So then that line is down here. It crosses at like -1. And then it's going to have slope 1, so it's got to cross like this. Oh, that's interesting. Okay, I see what's happening here. And then I'm going to draw this one in a close but not the same color. So this one, the one that'll go on the bottom, oh, these are wrong. X equals y minus 1. So this is going to be flipped. The area is going the wrong way. I should really switch those, but I'm not going to. I'm going to keep the problem as is, but it's probably going to come out negative. Like, no, wait, it'll come out positive. I know why, too. So this is going to be the same as add 1 to both sides, so y equals x plus 1 is your line, so it should cross at +1, and then you go up by 1 to add 1, and then go down by 1 when you subtract 1, so I'm just doing rise over run. So we're doing this cool little area right here. It's a paraboloid, if you remember those. Let's integrate this, see what it comes out as. I bet you it comes out positive because exponentials are negative, so, you know, there's that, unless you transpose them, so. Oh, and we did this one earlier. This should be easy. Okay, I believe in us. So from -1 to 1, and then I'm going to integrate with respect to x. So I'll just get e to the x plus y, because that's what happens. You just get it back. Evaluated from y minus 1 to y plus 1, and that's where this is going to get interesting. dy. I'm liking it. Okay, so now I'm going to be substituting in y plus 1 and y minus 1 in for x. So for this one, -1 to 1, e to the y plus 1 plus y minus e to the y minus 1 plus y dy. And I'm going to clean that up because that's going to be hard to integrate otherwise. -1 to 1, e to the 2y plus 1 minus e to the 2y minus 1 dy. Cool. Yep. If you're really weak at integrating, this one is going to be a hard one for you. Because I'm going to essentially make two sort of weird substitutions. So w is going to be 2y minus 1, and then dw will just be 2 dy, and I'll have to divide by 2. So for both these, I'm going to get a factor of 2 that's going to, and the 1's going to do nothing. So whether or not it was 1 or, sorry, -1 or +1 is absolutely irrelevant. You're just going to get a bunch of over 2's to fix this problem of I'm going to end up with a 2. This is very similar to e to the ax. I just end up with a 1 over a. So this will be e to the 2y plus 1 over 2 minus e to the 2y minus 1 over 2, evaluated from -1 to 1. If that was too fast for you, you can go through and do the two substitutions. It comes out exactly the same. Okay, putting in 1. So putting in +1, I'll get 2 plus 1 over 2 minus e to the 2 minus 1 over 2 minus, here's, I gotta be careful, e over 2, and I gotta put in minus 1, so minus 2 plus 1 minus e to the minus 2 minus 1 over 2. Yikes, I should have just took the over 2 out. Ugh. Okay. I did not leave enough space for anything. This is one of the problems of going online. Now I have like no space. So let's do a little bit of a cheat move. This first one gonna be a 3. This one's gonna be a 1. This is gonna be a 1 also. Isn't it? 2 minus 1? Oh, negative 1. This one's gonna be a negative 3. Ugh. This doesn't come out cute at all. Nothing combines in a good way. Poop. Guess we pull out our calculators to do this. 8.52458. That's frustrating. I was really hoping that one came out cute. I need to learn to not click my mouth on the camera. Okay. We are about 40 minutes in, which is usually where I stop and record it as a second lesson. I think you are good enough for right now. I'm going to pause and record this into two parts. Hope that's okay with you.